Strong acid, strong base titrations weren't too bad as far as calculations went because every 1 mole of H plus neutralized 1 mole of OH minus, and it was easy to see the number of moles of H plus when a strong acid completely ionizes. But for a weak acid like acetic, you won't get all of the protons it has to offer. It only partially dissociates unless you add enough base to make it. So when you're titrating a weak acid with a strong base, you have to take that into account, and the calculation changes a bit because of that. What I'm doing with this, I'm going to go through your notes totally, work through a practice problem sort of quickly. It doesn't cover everything, and then I have 2 more practice problems to post following that on weak acid strong base titrations, and I'm probably going to have either an example or a practice of a weak base strong acid titration, which is done similarly. But so that you don't have to watch all of it at once, we're doing this. The titration curves look a lot alike, and I'm going to look for examples of those too. We've got 4 regions of the curve. The initial where the pH graph is flat, between the initial and the equivalence point when the graph starts to go up. You're going to be using the acid-base neutralization reaction and the Henderson-Hasselbalch equation to calculate. I'll go through all of that in the examples and what you're doing when. At the equivalence point, your moles of acid and moles of base are equal, but because it's a weak acid and a strong base, you're going to get a pH above 7 because not all the acid will have reacted, but all the base is active. Once you hit the equivalence point, after that, the OH is just ripping the acid up, and you use the OH to calculate pH. So below where it says practice, and we're coming back to the practice, don't worry. We are coming back to the practice. How does this differ from strong acid, strong base? Your weak acid is going to have a higher pH because it's not completely dissociated. Your pH change in your rapid rise portion near your equivalent point is going to be smaller. So if you were looking at for your strong acid, strong base, you're going to see like a little wiggle, a little S shape for this one. And your pH at the equivalence point will be above 7 because it's a strong base and a weak acid. If you were to titrate weak base with strong acid, you would be above 7, or you'd be below 7 for an acidic pH, and your curve would go the opposite direction. You'd start off basic and drop down to acidic. So you're going to be looking at those graphs, I think, in one of the homeworks. Let's go on to that practice problem. I have it in a separate document, which I'll attach, and it's a bit long. So what I already did at the top, I figured out how many moles of acetic acid were in that sample, because the moles are going to be more useful in a lot of cases than the concentration. From Ka, I got pKa, because I know if I'm looking at a weak acid-base pair, I'm going to use the Henderson-Hasselbalch equation. So I'm looking for the initial pH right off the bat, and I will tell you, for these weak acids, you can pretty much ignore X. X is like dead to us. So what I'm looking at here, CH3COOH, what am I going to add to it? Well, nothing yet. It's just going to be breaking down into H plus and CH3COO minus. I have it written up here that you may see it as HC2H3O2 also. You can see those either way. Well, if I'm telling you faux show, I'm going to ignore X that's lost from my initial concentration of the acid, what I'm setting up my Ka equation with, which is all I'm doing here, is I'm going to say that this is 0.105, I'm ignoring X, and X is both of these. So what I'm going to always be looking for here, before anything is added, is that Ka equals X squared over my concentration of the weak acid. For our problems, and I can't think of any example where it would be practical for you to not ignore X with a weak acid, so you're always going to have this same setup. And for this case, it would be 1.8 times 10 to the negative fifth. When I solve through for X, you can see on your paper, I got X is 0.0013 molar. That's going to be my concentration of hydrogen. So my pH, negative log of that for 2.86. Straightforward to get a pH before I add anything. Volume of added base required to reach the equivalent point. Since the equivalent point is where moles of acid equals moles of base, I want to know when I have 0.00252 moles of NaOH in how many liters, because from my original molarity, it looks like, what am I adding? Let me go back to the other page with my problem. I would have 0.130 moles in a liter. That's all I would need to do to figure out my moles of base, or sorry, my volume of base. When I solve for that, I'm not going to work through this one, but I end up with 0.0194 liters. That's just your stoichiometry of reaction, moles of base equals moles of acid kind of thing. We've done something like that previously. So, nexto, we're going to add base. We're adding 6 milliliters of added base. When you get to this point, you need to think, am I at the equivalence point yet? So did I get to 0.00252 moles yet? Let's see. If I have 0.130 moles per liter, and a very tiny trickle here, 0.006 liters, how many moles of base am I getting? 7.8 times 10 to the negative fourth, I believe, moles of OH. Nowhere near my equivalence point. I needed 2.52 times 10 to the negative third, didn't make it. So the equation I'm looking at here is going to be my acid, which they have CH3COOH, plus OH minus is going to give me, and I don't care, you'll see this written with equilibrium arrow or with a single arrow. What this is going to give me is the conjugate base of my acid, and if you really feel like writing it water, but no one really cares about water, this makes this. So what you're going to see is that moles of OH, this is before the equivalence point, are going to be equal to your moles of CH3COO minus. Good. So what I need to do, and you can set it up as an ice chart if you want. It's more like the ICA, the initial change and concentration after kind of thing. I started off here, use moles. I started off here with 0.00252 moles. I put in 7.8 times 10 to the negative fourth moles there. Okay, cool. What's going to happen here is that this is going to be used up. I'm going to subtract it from here, and that 10 to the negative fourth makes it kind of nasty. It leaves me 0.00174 moles here, and that 7.8 that you added made 7.8 times 10 to the negative fourth moles of CH3COO minus. What I did, put in that many moles of this. I did not use up all of the acid, so it's subtracted out, made that easy. Henderson-Hasselbalch. pH equals pKa, which I already calculated, log of, which one's the base, 7.8 times 10 to the negative fourth, and the acid 0.00174. And calculate. It's given in your packet, again, at 4.392. So there's a small change. I'm adding base, so there you go. My log base over log acid. But I didn't yet get to the equivalence point. If you remember the pH from the beginning, check out your change. It should be logical. pH of 1/2, the equivalence point is always your pKa. Done. 4.74. That's good to know. pH at the equivalence point. When this is a strong acid or a strong base, we're like 7. No, because it's a strong base, it's going to be above 7. But this is okay. We can get through this, because what's going to happen, even though it's a little bit of a mess, is I added at my equivalence point. Follow along, we got this. So I've got 2.52 moles. We start off with CH3COOH plus OH minus, good, and it's going to make CH3COO minus, all good. So if this was 0.00252 and this is 0.00252, those canceled. but I still made 0.00252 moles of my base. Sounds good. So, I need it to be a volume, though, to calculate pH from it. I need to divide by my total volume. I started with 0.024 liters, and I added here 0.0194 liters. We calculated that already back above. That's just my total volume that I added. Because remember, I think step B. Divide by your total volume. What I end up with from here is 0.058 molar of that. So, moving on. Weak base, so not all of it takes protons from water. Yikes. I have seen these done differently. So we'll do this one this way, and I might have a cheaper way. I might have an almost cheat way to show you later. But this one walked me through it this way completely. So this would be the most accurate way because you're not going to say all of it takes. Some places I've seen say that this is negligible, and that's what I was hinting at. And to go with it completely, you will need a KB value. So for my KB, I would do KW over KA, and KB for this one, I've done this one so many times, it's 5.6 times 10 to the negative 10th. I've done that in every calculation known to man. So what I was saying about ignoring X, normally I wouldn't have even done all of these steps. I wouldn't have done all of this, and that's what I meant about later as I'm looking at it. It's the same thing as your first calculation then. I'm ignoring X. So KB is gonna be from here. But what we're looking at, let's put this in first, CH3COO minus plus H2O is going to give me, back to this acid, CH3COOH, plus OH minus. We're going back to there. But 0.058, okay, cool, X, and no one cares. What you're getting is back to what you did at the start. So at the equivalence point, we're doing KB, X squared, 0.058. You scroll down and see this, and I think it comes up clearer in the way I set the work up for the next one. This will give you your concentration of OH, which takes you backward, 14 minus the negative log of that, for your pH. Wow, that's long. I think we'll go past the equivalence point in my next example also to give you a better idea of what you're doing in each one. Please watch the next videos, at least the next one. They're all going to have examples that I think will come up a little clearer because I wanted this one to fit in the lecture too. So let's try a few more. See ya in a minute.